Welcome, everyone. Thanks for coming to attend our virtual seminar. One of, I forget how many we've done now this term, quite a few actually. So this is great. We've been having a lot of success, and we've had some wonderful speakers, and today is no exception. So I'm delighted to welcome Angelique Taylor, who is a PhD candidate in the Healthcare Robotics Lab at UCSD, working with Professor Laura Ulrich. And Angelique's research really lies at the intersection of a whole bunch of really interesting areas: computer vision, robotics, healthcare, and AI. So we're going to love the talk, I'm sure. And she aims to design algorithms that really allow robots to interact and work with groups of people. So human-robot team interaction, particularly in safety-critical environments. So super exciting stuff. Now, I'm going to list just a few of Angelique's awards, and there are many. So Angelique, I apologize in advance if I get any of the names wrong. This is a fantastic list. You've won so many. I have to, yeah, it's hard to read them all. This is really, really wonderful. So she is a National Science Foundation GRFP Fellow, an Arthur J. Schmidt Presidential Fellow, a GEM Fellow, Google Anita Borg Memorial Scholar, a National Center for Women in Engineering Technology, or NCWIT Fellow, Microsoft Dissertation Grant holder, and a Grace Hopper Celebration of Women in Computing Scholar. Whew, fantastic, so outstanding stuff. She received her BS in Electrical Engineering and Computer Engineering from the University of Missouri, Columbia in 2015, and her AS in Engineering Science from St. Louis Community College in 2012. And today she's going to finally, when I get through all my yapping, give us a talk about human-robot teaming in safety-critical environments. So without further ado, I turn the mic over to Angelique, and we are super excited to hear all the interesting things you're doing. Take it away.
Awesome. Thank you so much, Jonathan, for that lovely introduction. So as you said, my name is Angelique Taylor. I'm a 6-year PhD candidate at UC San Diego, and I work with Dr. Laura Ulrich. So our lab explores human-robot teaming in safety-critical, dynamic, complex environments, including hospitals, homes, and work sites. Our research themes include coordination and teaming, long-term learning, healthcare engineering, and machine perception. My work focuses on problems that robots encounter in human-robot teaming, such as perception of groups, social navigation, and interaction among groups of people. So in this presentation, I'll give an overview of the work that I've done throughout my PhD. The field of robotics is growing at a fast pace, with robot developments in everyday environments, such as hospitals, schools, and malls. On average, 70% of people in these environments are in groups. They walk in groups, they work in groups, and they interact in groups. Therefore, robots need a high-level understanding of groups to enable them to fluently assist and interact with us. However, most of prior research in the field of human-robot interaction has focused on dyadic interactions, which is interaction between one human and one robot. Also, they rely on overhead sensor systems, which cannot support sensing from a mobile robotic platform. In my PhD work, I designed perception methods to enable robots to work in any environment without having to place sensors everywhere. My work enables them to seamlessly work in teams, which will lead to robots that can work in safety-critical, real-world settings. One of the questions that I address in my work is how can robots work alongside people from both a perceptual and a decision-making perspective? The perceptual perspective explores how to enable robots to sense its team and track them over time. The decision-making perspective refers to concrete steps needed to effectively navigate and interact with teams. Today, robots are being deployed in the real world, which is dynamic and chaotic. Therefore, they need to act fast and perform accurately, especially in safety-critical environments. I addressed these gaps in projects that I conducted throughout my PhD. So first, I'll talk about my work on human group detection. In the earliest stages of my PhD, I was interested in problems robots would encounter when we placed them in environments where they needed to work side by side with people. One of the first problems they would encounter is how do you detect and localize their team members. However, group detectors have primarily been supervised and require significant computational resources, and many methods rely on these overhead sensor cameras. This led to my curiosity about how to design egocentric group detectors that are unsupervised and perform in real time in the wild where the environment is uncontrolled. To address these gaps, the goal of this work is to detect groups of people in real-world environments. I built the Robot-Centric Group Estimation Model, or RoboGEM. This is a high-level overview of the system. It takes RGB and depth data as input and outputs group clusters. So now I'll talk about each step of the system. People within groups tend to walk in the same direction. So I capture this by using optical flow, which is the motion of objects, which is represented by an X and Y vector between consecutive image frames, caused by the relative motion between objects in the camera. However, performance of optical flow is highly dependent on the degree of ego motion of the sensor, as it's often subject to large amounts of noise while the sensor is in motion. Thus, I need a method which provides dense optical flow vectors while reducing noise. So I used FlowNet 2.0, a neural network-based optical flow algorithm, which has been used for motion segmentation and action recognition. It uses a stacked FlowNet architecture and incorporates image warping to achieve smooth motion fields. This enables RoboGEM to decrease the amount of noise caused by the sensor and better detect people's motion. In order to detect pedestrians in the scene, I use YOLO, a state-of-the-art pedestrian detector, which has real-time performance using a GPU. YOLO divides the image into a grid, which generates a class probability map and bounding boxes with class confidences. Then it performs regression on these data to infer the bounding box coordinates. Using these bounding boxes, I extract pedestrian patches from the RGB depth and optical flow maps. Using these patches, I compute several features, which include the XY image plane location, which is the center column and row of the bounding box respectively, and the egocentric distance between the robots, which is measured from the depth pixels. And I measure the magnitude and direction of the optical flow vectors within a pedestrian patch. And then finally, I use these features to construct a feature vector for each pedestrian in the scene. I normalize these features and use them within a hierarchical clustering algorithm, which is parameterized by an inconsistency coefficient alpha, where a low value of alpha finds similar groups and a high value of alpha finds dissimilar groups. Hierarchical clustering starts by treating each observation as a separate cluster. Then it iteratively executes the following two steps. First, it identifies two clusters that are closest together, and then it merges the two most similar clusters. This iterative process continues until all clusters are merged together. Unfortunately, there are no publicly available data sets at the time of this work for egocentric group detection methods. Therefore, I performed a data collection in a local public park here in San Diego. So we mounted a Z stereo vision sensor on a double telepresence robot and let the robot roam around and observe people. This resulted in an hour and a half of video, which resulted in about 16,000 RGBD image pairs. And next we perform data annotation on this data. So we had two members of our team annotate a little over 14,000 image frames, which resulted in about 5,423 group detections. In order to validate our annotations, we employed validation consistent with popular computer vision benchmarks. So two members of our team labeled 2,000 randomly selected images, and we computed the precision and recall between their labels and found a precision of 0.83 and a recall of 0.79, which is consistent with popular computer vision benchmarks. In order to experimentally validate RoboGEM, I compare it to three methods. The first one is an extension of RoboGEM, which employs a post-processing step to RoboGEM, which is called the linear discriminant analysis based on L1 norm maximization. And the second method, I compared RoboGEM to a state-of-the-art supervised group detection method from the Spencer project. And finally, the third method compared RoboGEM to a group detection method by Solera et al., which employs correlation clustering in a structured SVM with their proposed G-MITRE loss function. I use standard measures from the literature to measure the performance. I also use an intersection over union or IOU. In these metrics, because this measures how much two bounding boxes overlap. Therefore, the first metric I use is accuracy versus IOU, which measures the accuracy of detection as we vary the IOU threshold. And because I use stereo depth maps to measure the egocentric distance between the robot and people in the environment, I measure the accuracy as I threshold the depth map. And next, I measure the log average miss rate, which is the miss rate on a log scale. And finally, I measure the precision and recall, which are standard metrics from the literature. In general, both versions of RoboGEM outperform the other two methods. Also in the table, the up arrow means higher is better. In the figure on the left, as expected, the performance of all methods degrade as the IOU increases because the overlap criteria becomes more strict. Our results show that RoboGEM outperforms Spencer by 10%, and it outperformed RoboGEM using LDA-L1 and detection accuracy by 1%, and also Spencer outperforms Solera by 20%. In the center figure, both versions of RoboGEM have a similar miss rate, precision, and recall, and they both outperform Spencer and Solera. This indicates that there is a high false positive rate consistent with the findings of Litter et al. In the figure on the right, the depth threshold, as the depth threshold increases to 0.4, which is about 10 meters, the performance of all methods improve. Both versions of RoboGEM outperform Spencer and Solera, and also Solera does not rely on depth data, so its performance is constant at an accuracy of 0.07. So this is a video of a demonstration of how RoboGEM performs. The green boxes show the ground truth, or what our annotators labeled, and the red boxes show RoboGEM's group detections. As you can see in the video, this is a very challenging problem for RoboGEM and for our annotators. We can see the boxes flickering a lot, and the group detections change as time goes on. So these are issues that I'll address in my future work. So after exploring the problem of group detection, I found that temporal information is important for more accurate group perception, as shown in the last demo. Thus, it made sense to build on this system by also tracking groups over time. I wanted to explore how robots can leverage egocentric perspective geometry and images to improve group tracking systems. I was also interested in how to leverage recent advances in deep learning to improve the performance of my system. In this work, I address a key challenge that RoboGEM face, which is that it does not take temporal information into account. A fundamental problem in object tracking in general is called data association. So data association is a key component in multi-object tracking algorithms, as it's used to associate objects between image frames. Traditionally, data association methods use positional data or handcrafted features or a combination of both to associate objects over time. But in recent years, researchers have explored the use of convolutional neural networks, or CNNs, to replace the handcrafted features as it boosted performance. More specifically, the CNNs were trained to re-identify people, which is well suited for data association as they aim to re-identify people at different points in time. Yet little prior work has explored the use of deep learning for group tracking. Thus, there's a potential for robots to leverage deep learning features to improve data association for group tracking methods. So the goal of this project is to investigate how to design a group detection and tracking system that performs in real time in real-world environments and can learn on the fly by leveraging person re-identification convolutional neural networks. I address this problem in two research questions. The first one is, how can a robot track groups of people from an egocentric perspective on a mobile robot in crowded environments where both people are in motion and the robot is in motion? Second, how can we leverage convolutional neural network features or activation maps to track groups? And how does that compare to handcrafted features? I built RoboGEM 2.0, an egocentric group detection and tracking system that runs in real time. I leverage the intuition that people within groups are spatially close to each other with a common motion goal. To capture this intuition in the group tracking algorithm, RoboGEM 2.0, the group detection algorithm uses 3 distance policies designed specifically for egocentric perception to cluster people into groups. This is a high-level overview of how the system works. The goal of the group tracker is to preserve the identity of groups of people over time. Their identity can be represented in several ways, such as a number or color, etc. In this presentation, I will refer to group identities as group track IDs. So RoboGEM 2.0 takes as input RGBD image pairs, and it outputs a group track ID for each pedestrian, or a -1 if they're not in a group. Now I'll discuss the technical details of each step. In the first step of the system, I extract pedestrian patches using YOLO as done in my earlier work. Then I employ Deep Sort, a state-of-the-art pedestrian tracker, which uses a person re-identification CNN for data association. Deep Sort employs two distance metrics, which represent distances in terms of motion and appearance. The motion distance metric measures the Mahalanobis distance between pedestrians' common states from time t to t+1. And the appearance distance metric measures the cosine distance between convolutional neural network feature vectors. And then it combines these metrics using a weighted sum of both of them. Then it employs a standard common filter to track pedestrians over time. Now I'll talk about the egocentric group detection algorithm. Consider a scenario where pedestrian I and pedestrian J have bounding boxes BI and BJ. The bounding boxes are parameterized by the X, Y, and width and height of the bounding boxes. I generate 3 n by n adjacency matrices to represent 3 distance policies where n is the number of pedestrians at time t. These policies include the width between 2 bounding boxes, the respective height ratio, and the ground plane distance between BI and BJ. Then I apply a different threshold to each adjacency matrix such that the element for BI and BJ is 1 if they're in a group, or 0 otherwise. In the final step, I run depth first search to find cycles in these adjacency matrices, and then that generates the group detections. So in the final step, I track groups of people using a group tracker. So the group tracker uses group data association to match previously seen groups with group detections. The group detections and pedestrian tracks are input to the group tracker, and the group tracker uses this information to match group detections to pedestrian tracks, and it aggregates the convolutional neural network feature vectors of the pedestrians within groups to be used as a similarity metric from time t to t+1. It uses the same tracking mechanism as Deep Sort, therefore a common filter is also used to update group tracks. Here's a demonstration of RoboGEM 2.0 running on a mobile robot on the data set that I mentioned earlier. So the red boxes show the individual pedestrian detections, and groups are identified with the same color bounding box and group track ID. So as you can see, it gets confused when the scene gets really crowded and when people move further away from the robot. But overall, the tracker performs pretty well. One thing I was really interested in exploring is how RoboGEM could be used in a real-world application, specifically human-robot teaming in healthcare. This is a dynamic setting in which teams experience coordination, communication, and decision-making challenges, rendering it a well-suited application domain for my work. I was interested in how robots might be used to reduce the number of preventable patient harm, which in the US kills over 400,000 patients annually in hospitals alone. 70% of these errors are a result of communication and collaboration breakdowns that occur in safety-critical teams. Nurses are uniquely positioned to identify and prevent such harm, as they are the frontline healthcare workers and primary advocates for patients. However, strict hierarchical structures and asymmetrical power dynamics prevent nurses from stopping the line of behavior that leads to patient safety risks as they work in teams. For example, physicians often penalize nurses who speak up when they make mistakes that cause patient harm. As shown in this figure, there are 3 settings of power structure, which include the operating room or the OR, the patient's bedside, and resuscitation. Nurses are at the bottom of this power structure for all settings. thus providing nurses with a mechanism to promote open and honest communication within clinical teams can empower them to prevent behavior that causes patient safety lapses and errors. Therefore, the goal of this project is to investigate how robots can leverage hierarchies in how robots can challenge hierarchies in clinical teams. This work has resulted in 2 publications, one of which won Best Paper Honorable Mention. I built on my prior work with RoboGEM to consider how it might be deployed in healthcare. I refer to this system as Robot Team Support System, or RoboTSS, which has 4 main modules: the group detection and tracking module, a group motion forecasting module, which refers to a new group motion forecasting method using inspiration from characteristic crowd movement patterns in the computer vision literature. And finally, the group the group interaction module, which refers to various methods to enable robots to work alongside people in teams. In this work, I explore how RoboTSS can support clinical teams to address challenges that stem from power hierarchies in hospitals. The work I'm going to present here was formative ideation work, which inspired the algorithmic work, which I'll describe later. I employed a collaborative research methodology where I allow users to shape my research agenda. In this way, participants actively advocate for themselves. Thus, after conducting some initial interviews, I came up with the following research question: how can I design RoboTSS to support and empower nurses and clinical teams? I recruited 7 participants throughout the United States. 5 of them are female and 2 are male with a mean age of 32.9. The years of experience range from 6 months to 15 years with a mean of 7.9 years. 3 of the participants are clinical educators and work in a university simulation center. And participants work at various institution types, which include teaching and non-teaching, for-profit, nonprofit, and also urban institutions. During interviews, I introduced RoboTSS to participants and showed them a video of it in action. Building on this, I also discussed relevant problems in the field, which could be useful for this work, like problems in computer vision, robotics, and machine learning. Then I asked participants open-ended questions to enable them to freely express themselves. Some of these questions include: what are some team-related challenges that you encounter on a day-to-day basis? And what are some examples of breakdowns in team performance? During the interviews, I recorded audio of the conversations with participants' permission. And once the interviews concluded, 2 researchers transcribed the interviews and iteratively coded them into hierarchies following grounded theory. Our participants identified 2 major settings of clinical teams, which include surgery and resuscitation. Surgery takes place in the operating room or the OR and has a strict hierarchy because the surgeon or the anesthesiologist are always in charge. Resuscitation, or a code, can take place anywhere in a hospital, and it refers to performing interventions to save someone's life, such as when their heart stops beating or or when they stop breathing. This is a flexible hierarchy because anyone in a hierarchy can take on different roles on the team. I found 3 overarching themes from this study. First, robots can serve as a neutral party to challenge hierarchical culture. Second, my participants envisioned a robotic crash cart, which can be used during codes to improve situational awareness for team members. And finally, participants expressed concerns about new robotic technologies, such as privacy and workflow integration, which are important to consider in design. So now I'll discuss each key finding. Our participants envision a robot that could work as a neutral party to challenge asymmetrical power dynamics with physicians. For example, Jessica talked about how in the OR, surgeons are the king and anesthesiologists are like the peasants. And when things go wrong, the surgeon blames them for it. So this also ties into other problems that participants mentioned, such as identifying mistakes by the team. For example, Lauren once told a surgeon that they touched their hair during a procedure, which can cause a patient to contract an infection. Instead of re-sterilizing, the surgeon said, let's just focus on the procedure. But it's the nurse's responsibility to monitor, identify, and correct these mistakes. So they will eventually get blamed for this. So as a result, participants envision a robot that can take on this role for them and deliver objective information to the team as a whole. For example, they envision a robot that can administer a checklist to the team and automatically identify mistakes as the team works together. And the next key finding is that participants envision a robotic crash cart that can help support decision-making during resuscitation. For example, Sarah talked about how team performance was greatly dependent on how often people perform a code. Therefore, participants envision a robot that can fill this gap in several ways. They imagine a robot that can autonomously navigate to patients' rooms when a code is announced in a hospital. And then they want the robot to walk them through a resuscitation algorithm in real time. Also, they wanted the robot to support flexibility in the patient's continuously changing health condition. And they wanted the robot to automatically open up the drawers whenever equipment was needed at a certain step of the code. And finally, once a code has ended, they want the robot to automatically restock the cart for the next time that a code is announced in the hospital. Another interesting idea that participants discussed is the idea of choreography generation, which refers to how the team moves seamlessly around the patient's bedside. Jessica talked about how this would be nice move away from it. Jessica talked about how it would be nice way to move more efficiently such that no one obstructs their fellow team members. In other words, patients envision a robot that can spatially coordinate the team members as they work at a patient's bedside. They also wanted it to provide a shared display with color-coded position pads on the ground as shown in this figure. And they wanted the robot to physically allocate multiple people with different roles throughout the procedure. In general, nurses were excited about using technology to empower them. However, they have concerns about placing robotic technology in clinical settings. For example, Rebecca, who works in pediatrics, talked about how people would not want to be recorded by a robot because healthcare workers try to do their best when treating patients, but sometimes with human error, things go wrong. Also, their patients are children, so parents understandably get upset and file lawsuits against them whenever things go wrong. As a result, healthcare workers might be afraid that parents will use this data recorded by robots against them. Through a collaborative design process, participants express how they would design RoboTSS to support and empower them in teams. It can preserve the output of group identifications or group detections, and additionally support them with 3 capabilities. First, participants envision that the robot can perform role management by assigning roles and keeping track of how roles change by providing a semantic label to represent each person. Second, they also want the robot to perform error identification and verbally alert the team when it identifies errors in real time. Third, participants envisioned that the robot could generate choreography and use a shared display as mentioned earlier in my earlier slide, where team members should position themselves around the patient's bedside and verbally alert them when someone needs to change positions. My research reveals that when designing robots in clinical settings, robot practitioners need to take into account that clinical settings are hierarchical. To improve team performance in healthcare, we need to flatten this hierarchy such that the team is more collaborative and open to constructive criticism because strong teams save lives. I found that my system can be deployed on robots to support this collaborative structure using findings from this study. The trajectory of my work thus far has focused on perception of human teams and how to deploy my perception systems in healthcare such that it could potentially empower them. Now I'm interested in identifying how to best deploy robots in safety critical environments, more specifically the emergency department. My lab has been working with a local emergency department here in San Diego, and from our discussions with them, we found that they wanted a robot that can deliver equipment to them when they need all hands on deck, if you will, as well as other delivery needs in emergency departments, as this is a non-value added task, which is a task that takes clinicians away from their primary job duty, which is treating patients. So my work looks at how we can explore this. The emergency department is a high-stress, fast-paced, safety-critical environment, which is frequently overcrowded, understaffed, and underfunded, all of which have become worse during the COVID-19 pandemic. To alleviate these challenges, I designed a social navigation system to enable robots to fetch and deliver supplies to emergency department workers. To enable robots to work in these environments, they need to understand the severity of a patient's condition in order to make intelligent navigation decisions. For example, if a robot observes a patient having a heart attack, it should avoid navigating near this patient as it might interrupt patient care. As a first step to address this problem, the goal of this work is to investigate how to design robots that can socially navigate under safety critical conditions where patients have different levels of acuity. In this work, I consider the following scenario. A healthcare worker is a user that requests supplies to be delivered by a robot. And the robot responds to this request and delivers supplies to the emergency department staff worker as quickly as possible. I explored this problem while considering two research questions. First, how can we visually model a patient's level of acuity? And second, how can an agent optimize this path to avoid locations of high acuity patients? I developed a social navigation system that enables a robot to deliver materials to emergency department workers while taking patient level of acuity into account. This work is inspired by recent advances in reinforcement learning, more specifically deep Q networks, which have outperformed human players in Atari games. My work is also inspired by recent advances in activity recognition on video data. And unfortunately, there are no simulation systems that enable researchers to explore the emergency department as an experimental test bed. Therefore, I built a simulation system in OpenAI-GEM, which is a toolkit for developing and comparing reinforcement learning algorithms. It supports teaching agents anything from walking to playing games like Pac-Man and Space Invaders. In the future, I plan to open source this system so that other researchers can build on it and utilize it. Another key aspect of the creation of this system is to use a DQ network. So the foundational work of Minna et al. Proposed a DQ network to learn a policy for Atari 2600 games, which surpassed human performance. DQ networks approximates a Q table by iteratively adjusting the network to the Bellman equation as a target for the network. The authors input raw pixels from a game screen into a convolutional neural network, which outputs a state action value. They use the state action value to choose the optimal action for the agent. This approach has several benefits, which includes that it uses a experience replay, which stores the agent's experiences in a replay memory. And the agent's behavior is based on ADA greedy policy, which employs a random strategy at probability eta and a greedy strategy at probability 1 minus eta. I developed a social navigation system that enables robots to deliver materials to emergency department workers. We call this the safety critical DQ network, or SafeDQN. SafeDQN employs reinforcement learning. And so the goal of the reinforcement learning agent is to generate a policy which maps states to action such that the agent maximizes its cumulative reward. The reinforcement learning models an agent as a Markov decision process which interacts with an environment through sequential states. At each time step, the agent takes an action and is given a reward based on that action. So in our case, states are locations on the map, and the actions are that it can move up, down, left, and right. And the reward encodes the level of patient acuity. The optimal action value function obeys the Bellman's equation as shown on the slide, where Q is a table that stores the state action value, which tells the agent what action to take at time t. And E is the expected value of a state at time t given some reward and action. And gamma is a discount factor, which corresponds to how delayed the agent is rewarded. So the goal of SafeDQN is to plan the shortest path from a starting location to a goal position while avoiding areas of high acuity patients as much as possible. So when designing SafeDQN, we made several assumptions. First, we modeled the emergency department as a discrete two-dimensional real-world environment as commonly done in the literature. Second, typically in emergency department, patients are being admitted, transferred, and discharged. Therefore, we assume a discrete number of patients are being treated in the emergency department at any given time. Third, when an agent moves from one position to the next, it observes a video of patient treatment at the next position. And finally, we assume that patients have stationary positions on the map as they're not frequently moved in the emergency department. SafeDQN models patient acuity using two intuitions. First, high acuity patients tend to require fast, precise treatment, which ultimately results in very dynamic motion by the emergency department workers. And second, high acuity patients tend to require treatment for more emergency department workers than low acuity patients. So we use videos to represent these high and low acuity patients. And SafeDQN measures the maximum number of people using YOLO, which reflects the amount of resources needed to treat a patient. And it calculates the relative motion in the video, which reflects the chaotic motion of healthcare workers as they treat patients. To capture this average motion, we use one of two methods, which include optical flow and a key point detector over the course of a video. SafeDQN employs a neural network which predicts the optimal action to take at time t. SafeDQN outputs Q values and selects an action with the maximum Q value, where the higher Q values correspond to the optimal actions. For a robot to function in the emergency department, it needs an accurate representation of real-world observations. However, to the best of our knowledge, there's no existing video data sets of the emergency department. Thus, we constructed our own data set composed of videos that reflect realistic conditions in the ED. These videos show day-to-day tasks of healthcare workers and reflect how dynamic, chaotic, and crowded it can be. We seek to test SafeDQN's ability to navigate among low and high acuity patients. To facilitate this, we follow evaluation procedures which employ similar methods such as random walk, greedy search, among others. So for example, we use random walk, which the agent basically takes a random action at each time step until it reaches the goal. And A-star search and Dijkstra are classic navigation methods used to find the shortest path. We employ several metrics that are consistent with prior work to evaluate SafeDQN. To understand the overall performance of each method, we report the descriptive statistics of the average path length, average cumulative reward achieved in each episode, and the average high and low acuity penalties. And finally, we evaluate it on 4 maps with different spatial constraints. So in the future, we plan to deploy SafeDQN on a physical robot in a medical simulation training center to evaluate the effectiveness of our system in real-world settings. And to the best of our knowledge, this is the first work that designs robots for safety-critical settings while considering the severity of patient conditions. Thank you all for being a wonderful audience, and I'll be happy to take any questions at this time.
Okay, wonderful. Thanks, Angelique, so much. And apologies for the technical glitch. It's these things. Welcome to the world of Zoom and virtual talks. At least it's not a projector failing, or the things that tend to happen in person talks, right? Something always has to go wrong, otherwise it wouldn't be a good talk. Okay, so thanks. I can poll the audience. Would anybody like to ask Angelique a question? I have a couple myself, but if anybody else would like to chime in, either on the chat or just by turning on your mic, please feel free. We'll open it up for just a minute.
I have a question, if I can jump in while we wait.
Of course, of course.
I was curious when you were doing your group object detection. I've noticed, when groups walk together, they part of it is proximity, but they also tend to walk in step together. Was that something that you considered, and how hard would that be to factor in?
So I think what you're referring to is gait. So basically how wide their step is and looking at the consistency of that. That's actually not something that we explored in this work, but I imagine that would be a useful feature to use since people tend to have the same gait when they walk together. It's actually not something that we considered. But yeah, that seemed like it would be a great thing to look at to help improve the performance, or at least explore if it could improve. So yeah, thanks for your question.
Excellent. Professor Shkurti,
Hey, John.
please go ahead.
Hey, Angelique, thanks for the great talk. I was wondering about the use of mobile robots versus non-mobile robots in hospitals. So some of the scenarios you mentioned, like restocking a station, that sounds like should be or could be managed by a mobile robot with some sort of manipulator, perhaps. But other tasks like coordinating teams of humans or recording what's happening and making sure that nobody forgets a step in the procedure, that seems like it could be handled by sort of a robot that watches the procedure, like an overhead type of mechanism. So I'm wondering about what are your thoughts about when is mobility necessary in these types of scenarios?
Yeah, thank you for your question. I would say that it would depend on the task. For example, for those situations where participants envision the robot that could monitor them and basically identify mistakes. For example, for that scenario, they envisioned that the robotic crash cart could take on that role. Since the crash cart is already there in the room, and they utilize the crash cart as they're treating the patient. Of course, there might be some concerns with that, like where is the crash cart placed? Can the sensor actually observe them? Are people occluding each other? So there are those kind of concerns. But I think for that type of task, our participants talked about how, okay, well, the cart's already going to be there, so why not just robotify it, if you will. So I thought that was a very interesting design that they came up with for that project, which I think could be a really exciting thing to explore in the future. So I think it will really just depend on the task. I think if it requires that the robot be mobile, then of course. But in some situations, like for example, the one you identified, it's not really necessary for it to be mobile for that situation. But if you could have a mobile robot that could, be stationary at certain points, you can kind of use that for both scenarios. So.
Great, thank you.
Excellent. Oh, okay. We have one from the chat from Mr. Matt Giamu. I'm going to read it. So let's see what he says here. Awesome talk. I find it fascinating that nurses you work with requested a choreographer robot, which I think of as a high-level coordination problem. Can you comment on how many of their requests for the operating emergency rooms were more low-level, like, for example, handling or holding or washing or disposing of tools? Or was the discussion more focused on higher-level planning or social dynamics in the emergency room or operating room?
Yes, thank you for that question. That's a really good question. I think so the way we kind of framed this work for them, we made it very high level so that they could kind of just freely express how they envision robots to support them. I think what you're referring to, these low level tasks, are things that they mentioned, for example, with identifying errors. So one of the key problems they mentioned was, for example, like the example I gave in the talk, like when someone like touches their hair or something in a sterile area, and someone kind of points it out and say, hey, you touch your hair, you should go re-sterilize. These are kind of like the human error that I was referring to earlier, right? So these are situations where they wanted the robot to kind of tell folks to, go wash their hands or go re-sterilize or whatever. So I think for the purposes of this study, like that was probably the most low-level thing that they mentioned. But otherwise, they were more high-level like tasks that they wanted the robot to do.
Okay, interesting, very, very interesting. The whole domain is actually interesting. So I might just sneak in a couple of my questions now, if no one else, or if I can get yeah, I don't see any immediately coming up from folks. So I'll sneak in my two. One was regarding the crowd tracking and detection. Do you have scenarios or situations the algorithm has to handle where a crowd or a group breaks? And so you might have mentioned like breaks in how, like sometimes I'm thinking like, I'm walking with 5 people and well, maybe no, let's say 10 people, and 5 of them go off to the left to go look at something, and then 5 go off to the right, and then they, the dynamics are such that they sort of split, almost like a flocking, and then they rejoin. And does the algorithm, is it able to deal with some understanding of the fact that the group has divided and come back together, or does it just say, you now are 2 groups, now you're 1 again?
Yeah, actually the way we handle that is we keep track of how long the robot has observed each person in the scene, and we also keep track of how long we track them in a group. And so, for example, like after X time steps, we say, okay, you're officially a group. And if we observe that they kind of aren't in a group anymore in the future, we keep track of the fact that we knew that they were in a group. And so when they come like back together, we kind of merge them. But that's kind of the best mechanism that we came up with so far for that. That was like a really big challenge because, people walk very chaotically, even in this data set, especially when you're looking at them from an egocentric perspective, the tracker can get really confused, right? So we kind of had to kind of think about these kind of mechanisms to help support the tracking. So that's kind of the thing that we came up with to do that.
Oh, great. Okay, and that's fantastic. I mean, I was thinking exactly of, similar things, outdoors or indoors, in like a shopping mall where people tend to, I know when I shop, I'm kind of, like, even though I'm maybe with a group, I'm kind of half dawdling off to go look in a window and then coming back. And yeah, it's almost a combinatorial problem of how many people can split and then reform, and is it the same group or not? So very, very interesting. Okay, that was one question. The second is a higher level question, if I can ask, and it's actually it's related to the question Matt asked in some sense. That is, if you could just speak maybe for 3 or 4 minutes about some of the well, both the benefits obviously and challenges of actually working with human participants and trying to get them to say important and relevant and useful things about robotics. So I'm thinking about nurses. They're clearly, as you noted, a group that, I mean, could really make use of this technology, but I think many of us would not know, myself included, would not know the first thing about how to actually select a good group for a study and how to actually set that up such that you were getting responses that were true, I guess, or valid. So if anything you could offer in that area on just how to go about even doing this would be really, really helpful.
Yeah, sure. That's a really good question. And thank you for asking that, because at that project was the stage of my research where I was like, okay, I have this tracking system, now what? So that was a very like exploratory project, and seeing like how nurses kind of envisioned like robots to assist them. And so I actually did this work in collaboration with a postdoc in my lab at the time, HeRo, and she has this kind of quantitative background, whereas I have like more of the computational background. So we kind of put our heads together to do this work. And I learned from her, right? So she's like, okay, first step, we gotta like go out there and like interview folks and try to understand like how we can design technology to support them. So we first started off by talking to an anesthesiologist here at UCSD, affiliated with the medical school. And we basically talked to him about, what are some of the big problems going on to try to kind of narrow down our scope, since it is exploratory. And he was actually the person that kind of helped us come up with this problem of empowering nurses, because he's like, I feel like nurses need the most support because they're always like patient facing, and they're always also the one to kind of get shut down when they, try to correct mistakes. And, that leads to patient safety risk, and people can get infections. It costs the hospitals money, it costs the patients money, and then the patients have to stay longer in the hospitals, and they might even die from these infections. So it was a really big challenge. And so once we identified that from some of our early participants, then we kind of started to refocus our attention on this problem specifically. And then from there, you know, it was just about kind of getting out there and talking to folks. We basically implemented like a qualitative methodology, a collaborative methodology, called grounded theory. Which you basically go out and you interview your stakeholders. So the people who you want to be your user group, or the people who you want to adopt your technology. And you basically go out and interview them, you record the conversations, and then from there you try to find themes. And so for us, we kind of did this as an iterative process. So like for the first couple of folks we interviewed, we did this process and like, okay, what are kind of the big high level problems? And then that kind of helped us ask more specific questions for the next participants, right? So for example, this problem of being shut down, then we can kind of ask more directed questions to later participants, but also asking them the high level questions too, to try to understand more broadly what the problems are. So that's pretty much how we kind of tackled this. And then like, so nurses and kind of healthcare workers are very low tech. So they're not very like experienced with like technology. I mean, they know healthcare technology, but like that's it, right? So we kind of have to explain to them like what robotics is and what machine learning is, and then thinking about like ways in which we can use existing systems that are out there for their purposes, like for their like to support them. And so we kind of showed them some examples of like what a tracking algorithm would do, or what a like object detection or object recognition system would do. And we're like, yeah, so like computers can do these things now. So in knowing this, how would you kind of envision like us to develop a system to support you and your needs? And then it kind of helped them kind of translate, you know, these problems that we're looking at in the AI field and kind of translating that to what they could potentially do for their work. So yeah, I hope that like answers your question. But yeah, that's pretty much how we approached this. And we got some really interesting feedback from our participants, which I think would be like really good, nice prototypes to help support these nurses in their daily workflow.
Yeah, fantastic. Thank you. That's extremely helpful. That's really great. Okay, we have one more, and I think we have time for just one more. So one more from the chat. Hannah Zhang asks the following. She says, really cool talk. Thank you. This might be a bit of a vague question, but do you have any thoughts or comments on the steps we need to take to get to a place where clinicians, users in general, can trust directions given by robots? And a follow-up quickly is, are there definitions like levels of autonomy for the depth of understanding robots have to have in different scenarios to qualify performance of such algorithms? That's a bit harder. I think she's thinking of potentially something like the SAE autonomy levels for vehicles. I don't know if there's anything like that for medical robotic applications, but maybe just in general, you can comment on what steps we need to take to actually get to a point where we can trust robots in a healthcare scenario to give us directions.
Yeah, that's a really good question. And it also came up during our study. So for example, some of our participants felt that, like, for example, if a robot tried to get a team to do like a checklist which they're supposed to do before doing a procedure, and checklists were kind of designed to protect the patient. And so whenever like physicians or surgeons try to skip this step, it's really nurses' responsibility to administer it. So when it's not done, they get blamed again. And so this was something that they were really concerned about. They were like, okay, well, it would be nice if the robot could just take on this role so I don't have to do it. But they were concerned that the physicians wouldn't want to do it. Like they wouldn't even listen to the robot. So this is actually a big open question to see if people would actually listen to the robot. That's actually an open question. I don't know yet, but hopefully this is something we can address in future work and looking at kind of compliance with robot instructions, especially when the robot's instructions are to protect the patient. Yeah, that's a big open question, but also a really good question. Thank you for that.
Okay, excellent, wonderful. Yeah, thanks, Hannah, for that question. I also don't know how to. Many of the robots that we put in hospitals and care homes, they're very, they look very personable, and I might be less inclined to take an instruction from a robot that looks very cute, and I don't know, maybe if it was really menacing, I don't know if I'd be more inclined. I'm not sure. Okay, well, all right. I think we're actually just at the end of the seminar time slot. So with that, I think we'll thank everyone, and thank everyone who was able to listen, and great thanks to Angelique for a wonderful talk. I'll clap. Other folks are welcome to virtually clap with their clappers on Zoom. Excellent, wonderful. So thanks, everyone. Just a reminder that we have another talk coming up. Is it next week, Hallie? Florian, is it? I'm just trying to think.
Yeah, it's next
December 3rd. Is our next?
Yeah, you caught me off guard here, John. I'll look it up.
Cool, right? Yeah, no, we do have a talk coming up on December 3rd.
Dieter Fox.
Dieter Fox, right. December 3rd will be Dieter Fox, so please stay tuned for that. And for those of us here, Angelique, if you have time, we're going to break off into some short individual discussions in individual group rooms. And for that, I believe we will switch Zoom calls. So we'll switch the actual Zoom call over to the individual. And thank you so much. Great talk. And we'll see you on the other side in about 30 seconds.